In this model of Chapter 5 on Basic Population Models, Module 5.5, I cover population projection, including the Leslie matrix, example iterations of this matrix, and population projection of Drosophila fruit flies. The Leslie matrix. Leslie in 1945 reframed the continuous time Lotka model as a discrete time model using matrix algebra. This model, known as the Leslie matrix, provides a numerical tool for determining growth rate in age-structured populations that can be used to study the transient properties of populations as they converge to the stable state. Before I introduce this matrix model, I will take 1 minute to present a quick refresher on matrices and matrix multiplication. Matrices are used in population analysis and projection to efficiently express and manipulate a set of equations that look like the following: a series of formula with variables and coefficients. The coefficients can be arranged in matrix form as rows and columns like the following, and the variables arranged in vector form like this. The multiplication then involves the elements of each of the rows times the elements of the vectors. For example, a11 times x plus a12 times y plus a13 times z equals a in the rightmost vector. Likewise, a21 times x plus a22 times y plus a23 times z equals b, and so forth. Matrices in population projection will look like this, where the coefficients are denoted f and p. Zeros are considered structural elements, and the elements in the two vectors denote population number by age at two different times. This will become clear in the next slide. The Leslie matrix is of this form, where the top row of the matrix contains the birth elements fx and the subdiagonals px are the survival elements for the different age classes. The number of individuals age x at time t plus 1, denoted nx, t plus 1, is the product of the matrix and the age vector containing the numbers at age x and time t, nxt. The birth elements are computed as follows, where mx and mx plus 1 denote the number of offspring produced by females age x and x plus 1 respectively. Here's an example iteration. A population is projected through time by first entering an initial number of individuals into one or more age classes and multiplying the Leslie matrix by the age vector through a series of one-step iterations. For example, consider a population with 3 age classes starting with this matrix and this vector. Multiplying yields this new vector based on the matrix multiplication and seen to the right for each of the elements. The numerical results of the first iteration are substituted in the left vector, which, when multiplied with the matrix elements again, yields new population numbers in each age class. Then this outcome in turn is substituted for the left vector and again multiplied with the matrix elements and yields the population numbers for the third iteration. This table shows the results of this hypothetical population projected over 20 time periods. The first column is time from 0 to 20. The next 3 columns contain the numbers in each of the 3 age classes. This next column is total number in the population over all of these 3 age classes at each time. And the next column is growth rate, which is the ratio of the number at time t plus 1 divided by the number at time t. And the last 3 columns contain the percentage in each age class at each time. This rectangle contains the results of the first 3 iterations shown in the last slide. Note that initially there were equal numbers of individuals in each age class, but after a few time periods, the largest percentage of individuals shifts to age classes 0 and 1, that is, the younger ones. There is a numerical pattern of convergence to a stable or fixed rate of increase and a fixed age structure. Note that this relatively simple projection model, there are several fundamental properties of populations that can be identified. The first is oscillations. The model projections show oscillations where both the growth rate and the age structure proportions wax and wane due to the lag in reproductive output. These oscillations are caused by the time required for newborn individuals to begin reproducing, such that when the proportions of the population in the reproductive age classes are maximal, births will surge, and growth rate will be at its highest. And when individuals are primarily in the non-reproducing age classes, the growth rate will be at its lowest. The second property is convergence. Convergence of both age structure and growth rates occur when births are spread out over at least two age classes. This means that the peaks and troughs in birth sequences are thrown together and thus smoothed out in the replacement process. The third fundamental property is ergodicity. That is, the property that the present state of a population is independent of its makeup in the remote past, and is determined only by the birth and death rates recently experienced. The fourth and last property is stability, which is a state when the age structure is unchanging because the fixed fraction of reproducing adults will generate a fixed number of offspring relative to the whole population. In this example, as a population approaches its stable growth rate, lambda equal 2.1, its stable age distribution, the SAD, is approximately 67%, 27%, and 6% in age classes 0, 1, and 2, respectively. Next, I present the results of a population projection for the fruit fly Drosophila melanogaster. This projection is purely theoretical because in the wild many constraints limit growth rate, including physical, like temperature, humidity, and nutrition, food shortages and quality, natural enemies, predators and parasites, and pathogens, for example. However, the numerical projection captures characteristics of growing populations that can be generalized. Moreover, at certain times, even natural populations of fruit flies may experience optimal conditions of resources for short periods and thus experience near exponential growth rates. In the laboratory, colonies of flies that are maintained under optimal rearing conditions, that is diet, mating, climate control, may also experience rates of population increase that approximates the rate shown below. I use matrices with the elements shown here for a 90 by 90 Leslie matrix in which we have age in these two columns from 0 to 90. We have stage corresponding to the age. The subdiagonal elements shown here in the top row of Fx based on the fertility Mx. This table contains the results of the Leslie matrix projection with age in this column, the number of individuals at age X at times 0, 10, 20, 30, and 40 days, and then the stable fraction in each age class at time t. This figure gives the stage structure of the population from 0 to 100 days on the x-axis and percentage in each of these different stages on the y-axis. The inset shows the convergence of the growth rate to lambda equal 1.3. Population at time 10 days. The Drosophila population increased from an initial number of 4 individuals to a total at 10 days of number at age 10 of 332. This is an increase of 83-fold for 10 days, or an average of 1.56-fold per day. Of this total number of 332 individuals, there were 52 eggs, 165 larvae, 111 pupae, and 4 adults. In other words, slightly over 1% of the population was in the adult stage and 99% in the pre-adult stages. Since the pre-adult stages are found either in fruit, that is the eggs or the larvae, or in the soil, that is the pupae, only a tiny fraction of the population, that is the adults, would be visible flying around. Population at time t equaled 20 days. In only 20 days, the population expanded by over 3,200-fold, from 4 individuals to over 13,000 individuals. The 10-day growth rate at this time was an increase of 40-fold, or a 1.45-fold daily increase. Across life stages, there were 5,300 eggs, 7,500 larvae, 180 pupae, and 213 adults in the population, which translates to 40% eggs, 50% larvae, and less than 2% for both the pupal and adult stages. Population at time t equal 40 days. In around 6 weeks, this hypothetical fly population exploded to over 3.5 million individuals, or around 40-fold over the last 10 days, and nearly a million-fold over the initial population size. This is equivalent to 20 population doublings in a 40-day period. At 40 days, the population is approaching its stable state with a daily finite growth rate of 1.3-fold and a stage distribution of 32%, 62%, 5%, and 1.5% of the total population in the egg, larval, pupal, and adult stages, respectively. These values are all quite close to the stable state described next. So the population in a long term, that is a stable state. The characteristics of this population when it has converged to the stable state include a daily finite growth rate of 1.3-fold and a stable stage distribution of 32, 62, 5, and 1.5% eggs, larvae, pupae, and adults, respectively. So two aspects of this projection merit comment. First, the fraction of adults in the population is extremely small. Inasmuch as this stage is typically the most easily sampled in the wild, using, for example, banana baits, observations of changes in the numbers of adults are not unlike the iceberg metaphor. In other words, 1.5% of the population of adults means that most of the population is out of sight. Second, with a doubling time of only 2 to 3 days, a population doubling from, say, 10 to 20 or from 50 to 100 may go unnoticed. However, several doublings from a few thousand flies can become millions of flies very quickly. Thus, what appears to be a sudden population explosion of flies may have nothing to do with changes in population growth rates, but it rather is an issue of detectability. So this ends Module 5.5 on population projection.